Okay, so quick review. Okay, work energy theorem says that work is a change in energy. Okay, mechanical energy. What we have to be able to do is say, all right, do I have work or do I have to calculate it? Okay, there's two ways to calculate it. Force times distance or change in energy, delta E. That could be delta EK if it's kinetic. How do we tell if it's kinetic? Yeah, the object will be moving, and even more specifically, the object's speed will change. Okay, a change in speed means a change in kinetic energy, which requires work. Okay, now the other side of that could be if there's a change in height. If there's a change in height, then we're talking about a change in potential energy. Okay, lifting something requires energy, it requires work. Okay, so those are the kinds of things we have to set up. Okay, now yesterday I stressed to you the importance of being able to picture this in your head. Okay, now maybe you're not a visual person. Okay, like picturing things in my head works for me. Okay, maybe you're like an auditory person. Okay, you'll probably notice that every time we do a question, I probably read the question 3 times. Okay, the reason I'm doing that is I'm trying to help the people who are more about hearing it, being able to get it sorted out in their head by hearing it over and over again. Guys, even when I do these questions for myself, like when I'm making up the key for your unit exam, okay, I visualize it, I read it to myself 2 or 3 times, okay, and then sometimes I even do this, I'll like mime it out. Okay, if you're a person who's like a kinesthetic type of learner, okay, where moving things around works for you, okay, do that. Okay, I've seen people that they've got their phone and their calculator on their desk, and there's no shame in that. It doesn't look like you're playing with toys. Okay, it's okay. It's whatever's going to get that picture in your head. Okay, about being able to see what's going on, so that you can understand the changes in energy that are required. Right? Okay, so let's have you guys try this one. Okay, we've done some like this already. This was actually the question that's like the rant I went on about, why it's important to go the right speed through a school zone or a playground zone. Okay, so it's very much like that. Okay, I'll read it out to you here. All right, I'd like you to write it down so that you have the full example. A car applies its brakes with a force of 10,000 newtons. Okay, it slows from 20 meters per second to 6 meters per second. If the car's mass is 1,700 kilograms, how far did it travel? Okay, and that would be how far did it travel before coming to a stop? Okay, I probably should have that in the question. How far did it travel? Or sorry, doesn't stop, sorry. Between 20 and 6 meters per second. Okay, how far did it travel between slowing from 20 to 6 meters per second? All right, I'm going to give you a little bit of time to copy that down and get started on it. Okay, and then I'll walk you through the first 2 steps. Okay. Okay, so in looking at the context of this question, so this is like the second time now that I'm reading through this question, okay, this car is applying its brakes. What do cars do when you apply the brakes? They slow down, right? That's what brakes are for. Okay, is that an acceleration still? Which direction is that acceleration? Negative. Now, if this 10,000 newtons worth of force is the force that causes that acceleration, which direction is this force? Positive or negative? Here's the weird thing, guys. As North Americans, we struggle with this because we use cars all the time. When you apply the brakes, you accelerate backwards. That's what slowing down is. Slowing down is a negative acceleration. We struggle with that because we picture accelerate backwards means go backwards. Luckily, brakes don't do that. Okay? Brakes only bring you to a stop. They don't actually cause you to move backwards. That would be really bad. Okay? But they still provide a negative acceleration because friction, that's what brakes use, is a negatively directed force. So if you did this question and you got negative 30.9, you only missed putting a negative on the 10,000. The 10,000 newtons is backwards. Okay? Now, in the end, it wouldn't be that big a deal, but I'm explaining to you why, if you got negative 30.9, why you got that answer. Okay, you basically did everything right, but this is one of those little twists that I'm throwing in there that we haven't done before. All right, let's look at the first two steps here. So brakes cause us to accelerate. Accelerations are changes in velocity. Changes in velocity require work. Agreed? Okay. If I'm changing my velocity or changing my speed, what kind of energy am I changing? Somebody said it. The kinetic energy, yeah. Okay, so I know already in this question the work that's being done, in this case by the brakes, is going to change the kinetic energy of the car. Okay, now my givens here are that I was told the force, okay, that's actually the force of friction, that's what your brakes use, 10,000 newtons. Okay, if you've never seen how your brakes work, okay, next time you're next to a car, just look in one of the wheels. You'll see this big shiny circle, okay, that is your brake rotor, and then you'll see this little kind of rectangular shaped thing that's kind of clamped onto it. That's the brake pad. Okay, and when you apply the brakes, the brake pad squeezes against the brake rotor and causes friction. Okay, it produces a whole bunch of heat. That's what your kinetic energy turns into. Your brakes turn your kinetic mechanical energy into thermal energy in order to cause you to stop. Okay, if you actually watch like racing that happens at night, you can actually see the brake rotors glow. Okay, they'll glow like a cherry red color because they get so hot when they're applied. It's kind of actually cool. You just see this red circle inside the wheels of the race cars. Okay? All right, so we got a force of negative 10,000 newtons. We have that it slows from 20 to 6. Which one's initial? The 20 is initial, yeah. Okay? All right, and that means obviously then the 6 is the final. All right. The car's mass is 1,700 kilograms. We're looking for how far it traveled. How far is distance? Okay, so I've probably read over the question about 3 times now. Okay, I've got my givens. I've decided what kind of energy is changing. Okay, am I going to have to substitute in force times distance for W? Well, if I'm solving for distance, I better have distance in the equation. Okay, and I was given force. So yes, I am going to have to substitute in force times distance for work, because they didn't say this many joules of work. Okay, so I have to figure it out. The change in EK means to take final kinetic energy and subtract the initial kinetic energy. In this question, none of those are 0. We did a few problems yesterday where one of the 2 energies was 0, and that kind of made things easier because we could just get rid of it. Okay? In this case, we can't. Do I have a formula that solves for kinetic energy? I do. Okay? On my formula sheet, it says that kinetic energy is 1/2 times the mass times the speed squared. Actually, not V, it's just V. Okay? Times V squared. All right. So can I plug that in for these 2 terms here? Absolutely I can. So I'm going to have force times distance equals 1/2 times mass times final speed squared minus 1/2 times mass times initial speed squared. Okay, everybody all right with that? Okay. Do I have all of those numbers except for D? I do. Okay. Now, have I written the same thing 3 times? It doesn't look the same, but I have. I said work is a change in kinetic energy. Then I said force times distance is final kinetic minus initial kinetic. Is that the same thing? And then I just expanded that out so I had the formulas in there. Still the same thing? That's what you do in a work energy theorem question. You start out with work energy theorem. Okay? Then you expand it out, and then you expand it out again, and then you manipulate and solve. It's always the same steps. Okay? All right, so I'm trying to solve for D. How do I get D by itself here? Well,
You have to divide force to the other side.
right, I got to divide both sides by force. Okay, divide this side by force goes away, and divide this side by force. All right, now I'm solving for D. I just have to plug in my numbers. All right, so I'm going to have 1/2 times 1,700 kilograms times 6 squared. Okay, that was my final. minus 1/2 times 1700 times 20 squared divided by negative 10,000 newtons. Now I'll get a positive distance. Okay? All right, so if I'm plugging all that in, I'm going to have 0.5 times 1700 times 6 squared. Okay, minus 0.5 times 1700 times 20 squared. All right. Now I need to divide by negative 10,000. All right, 30.94 meters. Okay. That's a long way. Okay, if I was hitting my brakes, I would maybe want to slow down faster than that, unless this is one of those situations where, oh, okay, the light's going to turn, you know, I'm going to apply the brakes and brake efficiently, and you know, if you have a hybrid car and you have the brake coach and it's telling you how good you did. Does anyone have that in their car? We have a plug-in hybrid and it's got this thing called a brake coach. I love it. It's a game to me now. Okay, when I'm slowing down, I slow down really slowly and efficiently, and that tells me I got 100% of the energy returned, which is a total lie, but it makes me feel good. Okay, but yeah, you can, in newer cars, you get this thing called a brake coach. It tells you how good your braking is. Okay. Questions on that one? Does it follow the steps we went over? Okay. Okay, so here's another one. Now, this one's a little bit different, but I'm going to tell you this little piece of information. A person is lying on the ground in this question. Okay, they're lying on the ground with a slingshot. They're going to draw the slingshot back 0.4 meters with 1,500 newtons worth of force. I don't know how they do that because that is a huge amount of force, but let's just say they do. Okay, the rock reaches a height of 30 meters. What is the mass of the rock? Now remember, this person is lying on the ground. What is the initial height? 0. Okay, the initial height in this question is 0. That's why I'm telling you the person's lying on the ground and aiming the slingshot straight up. Okay, that's one of those contextual clues that we've been talking about. All right, so in this question, we've got a slingshot aimed straight upwards. Okay, when you pull back a slingshot, are you doing work? Okay, so we know that definitely work is being done in this question. We just don't know yet which kind of energy it's changing. Okay, so as we read through the question, we're told that the slingshot's pulled back 0.4 meters. Okay, so that would, is that a distance or a height? It's a distance. How do we tell the difference?
Because the force is exerted to pull it back 0.4 meters.
Exactly. I read the question, and I see within the context of the question that that's not telling me this is a starting height. It's telling me the slingshot was pulled back this far. Okay? I have to read the question. I have to get it from the context of the question. All right? So D is 0.4 meters. All right? And it uses a force of 1,500 newtons. So I'm kind of sorting out my givens as I read through the question for the second time. Okay? The rock reaches a height of 30 meters. Okay, is that initial or final? It's a final, because what did we say the initial was? 0. The person was lying on the ground. Okay, so we know that the initial height is 0 meters. Okay, and we know that the final height is 30 meters. All right, we're looking for the mass of the rock. Now that's new. We've never had to look for mass before. We've looked for speed and force and distance and height, but we've never looked for mass. All right, so in this question, we're talking about shooting something straight up in the air. While its speed probably does change, that's not what the question talks about. It only talks about its change in height. So what kind of energy is changing here? Potential. Okay, so I'm going to say work is delta EP. Right? Since they give me force and distance, I'm going to substitute force times distance in for work, and I'm going to substitute in change in energy, that is EP final, minus EP initial for delta EP. Did I just write the same thing? I did. Mathematically, I'm still saying that work is a change in potential energy. Can I shortcut here? Is there anything I can eliminate? What can I eliminate? Initial potential energy. I'm on the ground. Can't fall any further. Okay? No potential energy on the ground because your height is 0. M times G times 0 is 0. Right? So I can get rid of this. For this situation, that's irrelevant. Can I plug in formulas now? Right? I'm kind of at that point, right? If I'm going to solve for the mass, I've got to get mass into this equation somewhere. I don't have it in there yet. So I'm going to say force times distance equals the final potential energy, which I calculate with M times G times H, in this case, H final. Right? Everyone following me so far? Right. So now I need to get mass by itself. What do I do? Well,
Divide it by gravity and final height.
right. I move gravity and final height to the other side by dividing both sides by that. Okay. So G times HF. Okay. That's going away. G times HF. Right. That's going to give me mass. Perfect. I've got my formula. Okay. I'm going to plug in my numbers. 1,500 newtons times 0.4 meters divided by 9.81 meters per second squared times 30 meters. That's going to give me mass. All right. So I'm going to take 1,500 and multiply it by 0.4. 600 joules. Okay, that's what's going on here. 600 joules worth of work. Okay, I'm going to divide that by 9.81 times 30. That is a big rock. Not the big rock, but it's a big rock. Okay, that's 2 kilograms. That's like putting a 2-liter bottle inside a slingshot and trying to shoot it. So, but this is also a massive slingshot because if I put all my weight on it, I couldn't pull it back that far. I only weigh 800 newtons. Okay. Don't figure out how much that is in kilograms. It's not a number I'm proud of. Okay. Now, does that make sense, everybody? 2.04 kilograms. Okay. All right. Now, if I was marking this, if this was an exam question, okay, here's where our marks would be. Mark for Gibbs. A mark for identifying work energy theorem and what type of energy was being changed. Okay. Another mark somewhere in here for your setup of the work energy theorem. Okay. A mark for your algebra. Okay, so we're up to 4. Okay, sometimes I give you a mark for plugging in the numbers. That could be 5. Always a mark for the answer. This is somewhere between 5 and 6 marks, depending on whether I decide to give marks for the number plugging, okay, or whether I'm just giving marks for the algebra and number plugging together. Okay, everybody with me there? Now, since these are patterned, okay, and we know the patterns we have to follow, are the first 3 marks of this pretty much a gimme? Pretty much. Okay? I get 3 marks for, well, I get 1 mark for writing down my givens. I get 1 mark for writing works of change in energy. And as long as I can identify that height's changing or speed's changing, I can get that mark. Okay? And then setting up force times distance equals, final minus initial. There's 3 marks. I haven't even done any math and I've got 3 out of 5. That ain't bad. Okay? Is it important to show your work? Okay, let's do this one and then I'll give you a little break. Okay, so on this one here, we're doing 4,000 joules worth of work. That's nice, they gave me work on this one. Okay, 4,000 joules of work is done on a 25 kilogram box, carrying it up a ladder from a height of 7 meters. What is the final height of the box? Okay, now the answer is there, so you can check it if you got it. It's 23.3 meters. Okay, give you a few minutes on that one before I spoil anything else. Okay, so if I'm reading this through now for the second time, okay, I've got 4,000 joules worth of work. So they outright told me W is 4,000 joules. Okay, and it's done on a 25 kilogram box. What does kilograms measure? Mass. Good. Nobody said weight. They don't measure that. Okay, 25 kilograms. Okay, and we're carrying it up a ladder from a height of 7 meters. So that would make 7 meters initial or final? Initial. It's from that. Okay, so that would be our initial height, 7 meters, and we're looking for the final height. Okay, given that information, height is changing. What kind of energy changes when height changes? Potential energy. Okay, so then I know that work is a change in EP. All right. Anyone want a couple more minutes on this before I go through the rest? Okay. So if I know that work is a change in potential energy, and they told me the work, this is a question where I don't have to substitute FD. Agreed? I can just put 4,000 joules in for W. All right, so I'm just going to continue to write W for now. Okay, but on this side, I am going to do this. Final potential minus initial potential. Now I'm looking for final height. Which one of those terms is final height going to be in? Final potential energy. Okay, it's going to be part of EPF. Okay, because it's what contributes to how much energy I have at the top of the ladder. We'll assume top of the ladder. Okay, now that means I want to get EPF by itself. Like before I put in all the M's and G's and H's, why not isolate that before it gets too busy? You can do it after, doesn't matter. Okay, but for me, I like to move things when they're small. Okay, especially now that I'm old, small things are better for me to move. Okay, so I'm going to take EP initial and I'm going to do what with it to move it over? Add it. Okay, now as I'm walking myself and talking myself through this, okay, and you notice I keep doing this because I'm crazy, okay, but that's what I'm doing in my head, okay, as I'm walking and talking myself through this stuff. I'm going to take work, which by the way is the change in energy, and I'm going to add it now to the initial potential energy, and that is going to give me my final potential energy. Well, gee, now that I've talked myself through that, that kind of makes sense. If I start out with this much and I add the change to that, I should figure out what I have at the end, agreed? It's always nice when something makes sense logically, okay? Makes the math feel better. Can I plug in my formulas now? I'm kind of at that point, right? I can't go any further until I have all the other numbers in. Okay, so I'm going to have work plus M times G times H initial. That's the formula for EP initial. Okay, equals M times G times H final. All right, I'm looking for H final. What do I do with the M and the G? Divide them over to the other side. Yeah. Okay, so that's going to get me final height. Okay, so now I can plug in my numbers. Okay, I'm all rearranged now. Okay, so final height is going to be 4,000 joules. That's my work. Okay, plus 25 kilograms, my mass, times 9.81, the acceleration due to gravity, times 7, the initial height. Divide all that by 25 times 9.81. Okay, so now if I punch all that into my calculator, okay, let's see what we get. So 4,000 plus 25 times 9.81 times 7. Okay, so that's my final potential energy. If I divide that by 25 times 9.81, 23.3 meters. That is a tall ladder. Okay, that must be one of those like fire truck extendable ladder deals. Okay, which by the way only reach to the 4th floor. Okay, if you live higher than that, the fire truck cannot rescue you with the ladder. If you weren't afraid of heights now, okay, but it actually is true. They do not reach past that. Okay, it's a weird thing. It actually affects house insurance. If you live in a condominium that's on the 5th or 6th floor, your insurance is higher because the fire truck can't reach you from there. And it's, yeah, strange. People sit around and figure this stuff out. And that's some people's job. All right, so we got 23.3 meters as our final height. Okay, did we do anything different on that question? We figured out what kind of energy was changing, we wrote down the givens, we set up work energy theorem, we put in the formulas, we manipulated them, we plugged in the numbers, we solved. It's always the same steps. Okay? All right, I said I was going to give you a little break after that one. So I'm a man of my word. I will give you guys a 4-minute break here, and then we will get going on a slightly different type of situation here. Okay, so like I said, small little twist, okay, not one that comes up often, but worth seeing. Okay, I have a toy car that uses a spring to propel it. So basically, it's like these carts that we used the other day. Okay, I just did what? When I pushed this in, what did I do? Work. Did I exert a force through a distance? That's exactly what's going on in this question. Okay, and then what they're going to do, okay, is they're going to set it on the floor. Okay, and they're going to let that spring release it. Okay, now in the question, the cart is already moving. I can't really replicate that here. Okay, but the cart's already moving, and then they release the spring, and the cart gets going. Okay, so we got the cart speeding up. Okay, as a result of a spring being compressed, okay, and then having that energy be released as work. All right, so the cart increases in speed. The spring is compressed 0.23 meters. I can't do that here. That's 23 centimeters. The spring's not that big on this. Okay, and the cart increases in speed from 1.2 meters per second to 3.1 meters per second. If the cart has a mass of 650 grams, what force is needed? What's the twist in this question? It's in grams. What does it need to be in? Kilograms. Okay? A newton is a kilogram meter per second squared. A joule is a kilogram meter squared per second squared. Kilograms is the mass. Okay? Always, always in kilograms when you're dealing with energy and force. Okay? So, how many kilograms in 650 grams? 0.650. There are 1,000 grams in a kilogram. There are 1,000 of anything in a kilo anything. Okay? That's how the metric system works. Kilo always means 1,000. Whether it's meters, liters, bytes, grams, all of it. Okay? That's the beauty of the metric system. No random imperial numbers to remember. Okay, I'll give you a few minutes on that one, and then we'll have a look at it. All right, so if I'm reading through this question, okay, I've got a toy car that uses this spring. We did the demo with the little dynamics cart there with the spring compression. If I compress the spring, I do work. Okay, when I release the spring does work. It does work on the cart. Okay, and what does it do to the cart? Makes it go faster. Okay, is there any mention of height? No, in fact, it makes mention of a level floor. Okay, it ensures that you understand there's no change in height here because the floor is level. Okay, so that right away establishes that in this particular question, the work being done is changing the kinetic energy. That's the contextual stuff I have to get from the question. Now, the actual numerical stuff I have to get from the question, okay, is that I have a spring that is compressed 0.23 meters. What did they give me there? Distance. Okay, and it increases in speed from 1.2 to 3.1. Which one's initial? 1.2, because it said it increases in speed. Therefore, the smallest one has to be the initial. Okay, these are all, things that are probably automatic to you, but things that I talk through to myself because I'm a little crazy, okay, when I'm doing these questions. So 1.2 meters per second, VF is 3.1 meters per second. Okay, if the cart has a mass of 650 grams, all right, we already talked about that, it has to be in kilograms, so the mass is 0.650 kilograms. All right, they want to know how much force was needed to compress the spring. Okay, so am I going to have to put FD in for W? Yeah, I have D, they want F, I definitely have to put FD in for W. All right, and I'm changing the kinetic energy, so that means EK final minus EK initial. Any shortcuts on this one? No. Nothing is zero here. It has initial kinetic, it has final kinetic. I can't cancel anything off. All right, at this point, I have to put the formulas in. Okay, I'm looking for force. Force is already on the board. Okay, I need to put in my formulas for kinetic energy on the other side. All right, FD equals 1/2 mass times the final speed squared minus 1/2 times mass times the initial speed squared. And then if I want to get force by itself, what do I do with D? Divide it over to the other side. Okay, so divide D, divide by D. Now I can plug in my numbers. All right, so F is going to equal 1/2 times 0.650 times 3.1 squared minus 1/2 times 0.650. I put 2 decimals in there. I only need 1. Okay, 0.650 times 1.2 squared. Divide all that by 0.23 meters. Okay, what do you suppose the most common mistake is here? Forgetting to square. Okay, most common mistake in work energy theorem questions. Okay, all right, so now that I've got that set up, I'm just punching in my calculator, 0.5 times 0.65 times 3.1 squared gives me that number, minus 0.5 times 0.65 times 1.2 squared. Okay, there's my change in energy. I'm going to divide that by 0.23 meters, the distance. All right, I'm going to have to use 11.5 newtons worth of force. That actually, for that spring that I compressed, that's probably about how much force I used. Okay, about 11.5 newtons. Okay, again, probably 5, maybe 6 mark question. All right. Now, today, we've done a lot where we were looking for force or distance. We did 1 or 2 where we were finding a height. We haven't done any where we were finding a speed. What's different if I'm finding a speed at the end? I'll have to square root because the speeds are always squared in that formula. Okay, it's the one little thing that sometimes people forget, and then they get a number that's way too big. Okay, if I've really taken my time to read the question, should I be able to recognize if I forgot to square root a speed? I should. Okay, if I get that, a kid's toy car is moving at Mach 2. Okay, that's 2 times the speed of sound. I probably forgot to square root something somewhere along the way. Okay. All right. All right. The last one. No, not last one. We'll probably do 2 more. Okay. Have you tried this one? Okay. So rubber band used to shoot a 0.135 kilogram marble along the floor. Okay. We're going to work with a rubber band tomorrow in our lab. Okay. So this is kind of a setup for that. Okay. And it mentions a level floor again. The rubber band is stretched using 300 newtons worth of force, and the marble starts from rest and reaches a speed of 18 meters per second. We're looking for how far we stretched the band. All right, give you a little bit of time on that one, and then we'll have a look at it. Okay. So when we set all this up, okay, we've got that change in kinetic energy because it's accelerating, it's changing velocity. We substituted in force times distance for W because we had force and we're looking for distance. We knew it was kinetic energy because it accelerated, but it started from rest. So we got rid of EK, and then we plugged in, solved for D, plugged in our numbers, solved for D. D is 0.0729 meters or 7.29 centimeters. Okay, so about yay far. That's actually a pretty reasonable answer, I would say, okay, in the real world. Always give it that last check. Give your answer that final common sense check, okay? If it said you pulled the rubber band with a small marble 10 meters, you probably forgot to do something somewhere along the way, okay? Or you messed up a number somewhere along the way, okay? Your answer should always make sense within the bounds of reality. Okay? I always do my best to make sure that answers come out the right way, especially on quizzes and tests. Okay. All right, questions on this stuff? Okay, let's talk about the plan here going forward. Tomorrow we're doing a lab, okay, on work. force times distance, that kind of stuff. Okay, it's pretty straightforward lab. You should be able to get pretty much all of it done in class even, so not a lot of homework on that one. Next week, we'll have another lab. Okay, it'll be on energy conversions. It's very similar to the acceleration lab. We're going to run a cart down a ramp. Okay, but this time we're looking at it from an energy perspective instead. So again, it's a procedure you kind of already have done, so you should be able to do it quickly, okay, and get a good start on the lab report in class. Okay, guys, I know you're tired. Okay, it's middle of May. You've been going hard since August. Well, okay, September. Okay, and you're getting worn out. We get it. Okay, I've been doing this longer than you've been alive. I have seen many grade 10 classes go through tired in May. It just happens. Okay, and that's all right. Okay, we're tired too, but we got to push through. Okay, this is adulting now, unfortunately. Okay, I'm tired, but I got to keep going. Here's how you can help a little bit. Okay, use your time effectively. Right? If I'm saying to you tomorrow when we do this lab, you should be able to get most of the lab report, if not all of it, done in class. If you're not, you didn't use your time effectively. And now you're going to have homework at home. I'm trying, guys, right now, going into June, to limit how much stuff you're going to have to take home and do for me. Because I want you reviewing for your final. Okay? Well, your Unit 4 exam. Okay? I want you to have time to do that. So I'm cognizant of that, and I'm pulling back on how much stuff I assign that you'll actually have to do at home. If you use your time effectively in class, you will have less of that to do. Now, here's the other recommendation. Time management. Okay? I know from looking at your labs, okay, that a lot of you leave them till the last minute. Okay? How do I know that? I can go into the version history and see when you worked on it. I know that sounds really creepy, but it's something that I do. Okay? And I see that, oh crap, it's like midnight on the night before it's due. It's due at 8:30 in the morning, and you're hurriedly finishing the thing up. That's the kind of stuff that tires you out. Okay? When you have to go, all right, I gotta be locked in now for like 3 hours to finish my English paper that's due tomorrow, and CoderreScience lab report that's due the next day, and I gotta be locked in for 3 hours. That's gonna wear you out. Honestly, that'll wear you out. Now, if you break it up into some more manageable chunks, and you go, okay, you know what? I'm gonna take 10 minutes during scheduled help today, and I'm gonna get the design and hypothesis done for CoderreScience lab. Okay, that's off my plate now, I just have to do this other little bit. Maybe I'm gonna write the introductory paragraph for my English paper while I'm on the bus, or, you know, or when I first get home, I'll take 10 minutes or 20 minutes, I don't know how long does it take to write an introductory paragraph, I'm gonna do English. Okay, and you do that. If you're not sitting down and having to be locked in for hours at a time, things don't seem quite so insurmountable. Okay, so time management is going to be the key for you going forward in the last 6 weeks here. Okay, and I say 6 weeks because I'm including the exam time. All right, so we're going to finish this unit up. We're going to be done, ready for the exam on May 27th. Okay, I will put out a review package next week sometime, okay, for the unit exam. Then we'll have our last unit. Last unit is short. Okay, it's only we're gonna have 10 days to do it. I've taught it in 4. Okay, 10 days is gonna seem like a long time to do that. There's one in-class activity in that unit coming in for marks. That's it. That'll be the last thing that you hand in to me for marks. Okay, it'll be due somewhere in like late in the first week of June, early in the second week of June. Okay, but it's something you should be able to get done in class. I'll put a review package for the Unit 4 exam up. You'll have the Unit 4 exam somewhere between the 12th and the 10th or 12th of June, somewhere in there. Okay, that should give us 2 days to do final exam review. I will post a final exam review package somewhere between the 12th and 14th of June on Google Classroom. You'll have that to study. Okay, we should, like I say, get 2 days, I think, for final exam review. If we go quicker, maybe we get more than that, but I'm gonna say probably 2. I am gonna try, once we get the supervision schedule and where all the exams are being written, if I can find a time, I'm gonna try and make like a morning or an afternoon where I'm available, and if you wanna come in and get some help or answer some questions for the final exam, that you can do that. Maybe I'll do some final exam review stuff if I can find a time where that's available and I can make it work. Okay, so that's the plan going forward. All right, like I say, manage your time here. Okay, start looking ahead to when things are happening. We should have a final exam schedule for you guys late this week, okay? Maybe early next week at the latest. Right? We've seen the draft already. They just have to, they give it to us and then we double check to make sure, they didn't double book Science 10 and Math 10C on the same day or something. And so we get a week or so to check that out. We've seen it, okay? So it should be finalized pretty quickly, right? And then you'll know. Everybody with me there? Okay, so that stuff's coming up, okay? Keep using Google Classroom, okay? You're gonna get everything well ahead of time, okay? Today, I'm actually gonna throw everything into Google Classroom and schedule it all, so it comes out according to what I just told you, okay? And then you'll be able to, oh, Mr. Coder posted that, I should probably pick away at that, 15 minutes here, 15 minutes there, okay? Do it that way as opposed to so much being locked in. Okay? Also, am I available for help? Come and see me, okay? If you are struggling with something, there is no shame in that, okay? Physics can be challenging, right? It's fun, but it's challenging, okay? I get it. If you're having trouble, come and see me, okay? Those are all my help times. I have no life, okay? You can come and see me anytime, okay? And also remember, any overdue assignments, I need them by June 14th at 3:20, okay? If you want them to be included in your grade, that is when I have to have them by. Alrighty? Questions from you guys? Okay, take a deep breath now. Let it out, okay? You're gonna be just fine, okay? I know you're tired, but you're gonna be just fine. All right. We're done. Good job today, guys.